In this video, we're going to think about the slope parameter in simple linear regression. And we're going to use a different example in this video. So this is an experiment where they measured 161 plots. The researchers measured 161 plots over a 10-year period, and they looked at the stability of plant biomass production. And that's what the response variable is here for these plots. And then they also measured the initial number of plant species assigned to the plots. So that's what this variable is here. And the idea was that as species number treatment increases, then so too does the ecosystem stability. So that's our data, and what I want to do is I don't want to dwell on all these formulas here. That's not what I want my focus to be in this video. But if you want a deeper understanding into what's going on, it can be worthwhile just spending a little bit of time replicating these results so that you can see where all the different pieces fit together. But I want to skip ahead to using the LM function to fit our simple linear regression model, and then look at the summary output to think about the slope parameter. So here's the estimated y-intercept, and here's the estimated slope, and so that tells me what the formula for this regression line is. So we're now going to think about the usual statistical inference problem of recognizing that we just have a sample, but what we're really interested in is the population from which we obtained this sample. And so in particular, we are wanting to do a hypothesis test for the slope in the population. And our null hypothesis is going to be that the population slope is 0, and the alternative hypothesis is that the population slope is not 0. And the reason that is of interest is because if the population slope was 0, that would imply there's no linear association between the response variable and the predictor variable. And so that would kind of make the whole analysis that we're doing a little bit redundant, because if there's no linear relationship there, we can't make use of that. So this is a useful test to do in simple linear regression, because if we are able to reject that null hypothesis in favor of the alternative, then we do have something to work with. It means we have established a linear relationship between the two variables, and we can use the predictor variable to predict the response, for example. Okay, so we've done step 1 of the hypothesis test. We've stated the hypotheses. Step 2 is to calculate the test statistic. So that's what a lot of these details are, is calculating it from scratch. Instead of doing that, we're just going to read it off the output. So it's in the row that's labeled with the name of the predictor, and it's in the column that's labeled t-value. So it's a t statistic, 6.742. Next step, step 3, calculate the p-value associated with that test statistic. So we could do that by hand using this code, or we can just read it off the output here. So the p-value, the two-tail p-value, is 2.73 times 10 to the minus 10. A very small number, essentially 0. That brings us to the 4th step. So the 4th step is make a decision, draw a conclusion. So because 2.73 times 10 to the minus 10 is less than a significance level of 0.05, we reject the null hypothesis in favor of the alternative hypothesis and conclude that the population slope is not 0. In other words, we've established a statistically significant linear association between log transformed ecosystem stability and species number treatment. Another way we could consider this is using a confidence interval for the slope. So again, we could calculate that by hand, or just as in the last video, we can use this confint function. So we're 95% confident that the population slope is between 0.023 and 0.043. We can also run the ANOVA command on the fitted linear model object. And if we do that, we get this analysis of variance table, this ANOVA table. So this is something that we looked at in the last lesson. But it turns out that the ANOVA table is also relevant to a simple linear regression model, and it gives us a different way of testing the slope. So I'll just run through this quickly. The first step is the same. Null hypothesis is that the population slope is 0. Alternative hypothesis is that the population slope is not 0. Second step is a test statistic. So in this case, the test statistic is an F statistic, 45.455. Third step, calculate a p-value. So 2.733 times 10 to the minus 10. You might be thinking, well, hang on, that's what we got last time. It is no coincidence. We'll get the same p-value for whether we do a t-test or an f-test when we're looking at the slope in a simple linear regression model. Given that, our decision and conclusion will be exactly the same as well. We'll, in this case, reject the null hypothesis in favor of the alternative and conclude that the population slope is not 0. There is a linear association between these two variables. The other thing that's useful about this analysis of variance table is it gives us a way of summarizing the fit of the model. And so I'm going to pick off some values here that we're going to use. So in this column labeled sum of squares, we've got two numbers. This first one that is labeled with the name of the predictor, in this case, is what's known as the regression sum of squares. So I'm going to pick that number off using this code here. So all I'm doing here is I'm taking the ANOVA table and I'm picking off the number that's in row 1 and column 2. So row 1, column 2 is this number here. So that's the sum of squares for regression. And then the sum of squares for residual, or the residual sum of squares, is given by the second row, second column, this number here. So I'll pick that number off too. And let's just correct that little mistake here. There we go. And then if I add those two sums of squares together, I get the total sum of squares. Okay, so what I'm going to do is I'm going to put those numbers together in the following way. I'm going to calculate 1 minus the residual sum of squares over the total sum of squares, or equivalently the regression sum of squares divided by the total sum of squares. So I'll just show you that both of those calculations give you the same thing. Okay, so what am I doing here? Okay, it's perhaps a little bit easier to think about this formula. So this is r squared. It's sometimes referred to as the coefficient of determination. Let's imagine a couple of extremes. Let's imagine that we had a perfect model. with no error. So instead of these points scattered around the line, as in this case, all the points lay along the line. So imagine a scenario in which that was the case. So in other words, I've got perfect predictions and there's no error in my model. The residuals are all 0, and so when I square them and I add them up, I get 0. So if this number was 0, the value of r squared would be 1. So that's the highest that r squared could be, and it would be equal to 1 if there was no error, if all my points could be predicted perfectly. So that's one extreme. Now let's think of another extreme. Another extreme would be if my regression line was flat. If my regression line was flat, what would that imply over here? So maybe let's look at this version of the equation now. The regression sum of squares divided by the total sum of squares. If my regression line was completely flat, then my regression sum of squares would be 0. The reason is because in that case, if my regression line was horizontal, the total sum of squares would end up being exactly the same as the residual sum of squares. And so the regression sum of squares would have to be 0 to make this equation work. So that's the other extreme. R squared is 0 when there's no linear association between the response variable and the predictor variable. So those are the two extremes. R squared is 0 when there's no linear relationship, and r squared is 1 when there's a perfect linear relationship. And so that's how r squared is a measure of model fit, because the closer the value of r squared is to 1, that tells us that the observed y values are closer to the regression line, and there's more evidence of a linear relationship between the two variables. So often, instead of having to do all those calculations, so having to figure out the analysis of variance table and then doing all these calculations here, and calculating r squared by hand, if instead we look at the summary, you can see that r squared is given here. And if we want to pick off that particular value, we can just use this code here, and that tells us the actual value. So I've shown you how to calculate the value of r squared, and then I've just shown you how to obtain the value of r squared if you don't want to actually go through all hand calculations. The most important part of this, though, is to interpret the value of r squared. And what r squared is telling us is the proportion of variation in the response variable about its mean that can be accounted for by this simple linear regression model. And so a better model will be able to account for a higher proportion of the variation in the response variable, and a worse model is not able to account for as much variation. So it's a useful number to calculate and to report on, but in isolation it it's not perhaps as useful as you might think, because this is actually a nice illustration of this. The value of r squared here is only 22.2%. So you might think, well, this model is only able to account for 22.2% of the variation in the response variable. It can't be a very good model. Yet, earlier in the video, we determined that there was a statistically significant relationship between the response variable and the predictor variable. So this is a case where we've determined that there is a relationship here. It's not a very strong relationship, because the model is only able to account for 22.2% of the variation in the response variable. So while r squared is a useful number to report on and interpret, it's not perhaps as revealing as we might hope. So there's still a few more things to talk about with simple linear regression, so we'll go on and talk about those in the next video. We'll talk about some things to watch out for and some possible pitfalls when we're using simple linear regression modeling.